Hello, thank you for the opportunity to present our work. I am Narasimha and I work at Cancer Registry of Norway. I'm happy to talk about our work titled A Decentralized Architecture for Secure Statistical Computations on Distributed Health Registry Data. This work is done in collaboration with my senior colleague Jan, who is the head of Registry Informatics department at the Cancer Registry of Norway. Some people may not have heard about cancer registry, so I would like to start with what is a cancer registry? A cancer registry is an information system designed for the collection, storage, and statistical analysis of data on persons with cancer. Registries play a critical role in cancer surveillance, which tells us where we are in the efforts to reduce the cancer burden. Cancer registry data may also provide data for cancer research and are used to plan and evaluate cancer prevention and control interventions. For example, health officials, researchers, and others use cancer surveillance data to answer questions like, are more or fewer people getting colorectal cancer this year compared to last year? Or which groups of people are most likely to get skin cancer? Cancer registries in the Nordic countries have a long tradition of cooperation and presenting cancer statistics on a Nordic level. The consortium is called NordCan. If you look into the NordCan architecture, currently all data are pre-processed and aggregated locally at the cancer registries before the anonymous data transferred to a central location at the International Agency for Research on Cancer, where the data is accessible to everybody on their website. The key challenges in the current architecture is that the data collection process is manual and cumbersome. As with all manual processes, there are high probabilities for errors to happen. Furthermore, high trust is assumed on the local pre-processing as well as the centralized entity for correct statistical computation. Finally, privacy is of utmost importance, and errors in pre-processing or security breaches at the centralized entity can have severe privacy impact for the patients registered at the cancer registries. These challenges in turn motivated us to ask the following research question. Is it possible to build a practical decentralized architecture with sound security and privacy guarantees among the consortium of cancer registries to perform statistical computations on distributed health registry data? We looked into the existing related works that specialized in avoiding personal data sharing between the organizations. There are two popular approaches in the related work. The first approach is the semi-centralized approach. In this approach, a centralized trusted coordinator sends the code to individual cancer registries and collects the results after the code gets executed from the respective registries and performing the final computation on the obtained results. The main problems with this approach are high trust needs to be placed on the coordinator, and the coordinator can suffer from a single point of failure. The second approach is the decentralized solution, where cryptographic techniques such as secure multi-party computations have been used to compute joint statistical functions. The main problems with these approaches are the lack of query authentication and authorization framework. Furthermore, the architecture design considers only weaker threat models or only limited statistical functions are computed, especially when homomorphic encryptions are used. Our solution should have the following set of requirements. First, we need to make sure that the incoming queries are valid and verified before it gets executed. To this end, we need good query authentication and authorization mechanisms. Second, we would like to have a decentralized trust to avoid a single point of failure, such as in the semi-centralized approach. Third, we would like to provide the capability to the end users to verify the correctness of computation. Furthermore, we would like to provide the capability for an external auditor to verify the transactions that led to the final computation result. Additionally, we would like to have the capability to detect misbehaving cancer registries to hold them accountable. Finally, data confidentiality should be protected during the persistent storage and the computation of joint statistical functions. To meet these requirements, we rely on 5 building blocks. The first building block is the consortium blockchain, such as Hyperledger Fabric, which records all the transactions happening in the system before, during, and after the joint computation. And the recorded transactions are stored in the immutable ledger available to all the members of the consortium. The second building block is the private IPFS network, which provides a decentralized storage platform for hosting the Docker containers containing the queries to be executed. The third building block is the TUF framework, which provides authentication capabilities. The fourth building block is the ciphertext policy attribute-based encryption, which provides authorization capabilities. The final building block that we rely on is the secure multi-party computation protocols, which provide the capabilities for executing decentralized statistical computation. In our system model, we assume that we have a consortium of cancer registries. Each cancer registry has extracted the target datasets from the master datasets depending on the offline request of the researchers. Each cancer registry has encrypted the extracted datasets and provided its keys to the researchers. The researcher writes a query for each member of the consortium and packages the query along with the key in the Docker container. The overall goal for a researcher is to compute joint statistical functions that are definable by arithmetic circuits. In our threat model, a researcher can create malicious queries to reveal more information than required and launch a denial of service attack by continuously bombarding queries to exhaust resources at one or more members of the consortium. The keys with the researchers can be compromised, which in turn makes the extracted datasets located at cancer registries vulnerable. The corruption can occur to minority number of members of the consortium during the execution of the computation. In short, we consider adaptive adversary, and the nature of corruption is semi-honest. Furthermore, the minority number of members can launch a collusion attack during the execution of the computation to infer more information. Our setup introduces a bunch of components to each member of the consortium to build a decentralized infrastructure to meet our requirements. First, API gateways are set up to provide entry points, and each API gateway in the cancer registry has a throttling budget for the incoming queries from each researcher. Second, the local health registry data are encrypted using a ciphertext policy attribute-based encryption algorithm. The public key associated with the encryption algorithm is distributed to the researcher in the offline mode. Additionally, the attributes for the researcher are agreed between each cancer registry and the researcher in a secure offline fashion, along with the datasets needed to answer the researcher's query. The authorization server uses the master key attributes from the researcher and the data extracted for the researcher to generate the ciphertext. The generated ciphertext is stored in the persistent storage system. Next, IPFS nodes are set up in each member of the consortium to form a private IPFS network to host the Docker images containing the query code. Additionally, we install Hyperledger Fabric nodes and appropriate smart contracts in the nodes for each member of the consortium to form the blockchain network. We create 3 channels in the blockchain network. The first one is to keep track of the task status. The second channel is to execute MPC protocols among the cancer registries. And the last channel is to store the metadata files and the public keys associated with the Docker images. Furthermore, a TUF authentication server is set up for verifying the correctness of the metadata files and the public keys associated with the Docker images. We also set up a node application server to act as a local coordinator to coordinate the different events happening at each member, such as downloading e-files and interacting with other local components. We also have an in-memory database that holds the plain text with a short retention policy to feed the MPC protocol in the blockchain network. The MPC blockchain client is set up to invoke the appropriate smart contracts and feed the smart contracts with the data from the in-memory database. The first step in the workflow is to prepare the query in a way that it can be authenticated and authorized. The researcher prepares a Docker image containing the query code that needs to be executed on the datasets of each member of the consortium of cancer registries. The purpose of the query code in the Docker image is to select the input datasets for executing the MPC protocol for each member of the consortium. If there are n members in the consortium, then the client prepares an n Docker images. Additionally, we use the Tough framework to secure the query and associated parameters in the Docker container for each Docker image. Tough framework uses 4 metadata files for each Docker image to create verifiable records about the state of the Docker image at a specified time. Each metadata file has a public-private key pair. The private key of the metadata is split into 2 shares using the Shamir secret sharing algorithm. The first share is for the researcher to contribute to the signature of metadata files, and the second share is for the cancer registry to contribute to the signature of metadata files. Docker images are pushed to the private IPFS network made up of IPFS nodes contributed by the members of the consortium, and the content ID of the image is used as a response. If the researcher or any consortium member tries to make changes to the pushed images in the repository, then it will be detected by all the members of the consortium. The signed metadata files and the public keys are pushed to the Fabric blockchain network. The mapping between the metadata files, public keys, and the Docker images are created through the content ID returned from the IPFS network. The immutability property of the blockchain network guarantees no further changes to the pushed metadata files and the public keys. Furthermore, for each push, the researcher and the appropriate consortium member needs to sign the files. In other words, the queries are already code reviewed by the appropriate consortium member before it is pushed to the repository. So in step 2, the researcher uses the client application to send the content ID of the Docker image to all the API gateways in the consortium. Each API gateway in turn forwards the request to the corresponding node application server and creates an open task in the Hyperledger Fabric so that the status of the tasks can be tracked transparently by all the members of the consortium. In step 3, based on the content ID received from the previous step, the node application server fetches the metadata files and public keys that are indexed by the content ID from the blockchain network. And node application server forwards the metadata files and public keys to the Tough authentication server, and Tough authentication server in turn verifies the metadata files and the public keys. If the verification is successful, then we move to the next step. In step 4, node application server fetches the Docker images associated with verified metadata files from the IPFS network. After fetching the files, the node application server executes the instance of the Docker image and passes the query parameters to the ciphertext policy attribute-based encryption authorization server. And the authorization server verifies the query parameters, decrypts the ciphertext, writes the plain text to the in-memory database, and sends the successful response back to the node application server. Afterwards, the node application server requests the MPC blockchain client to fetch the plain text from the in-memory database, and MPC blockchain client fetches the data and invokes the appropriate chain code to execute the multi-party computation protocol. The protocol is executed through the Fabric network such that the data confidentiality of the individual cancer registry is protected. After the successful execution of the MPC protocol in the blockchain network notifies all the API gateways of consortium members about the successful execution, and clients can query any API gateway available in the consortium to retrieve the results from the blockchain network. Since the final results are persisted in the blockchain network, the client can also check if the results are the same across the cancer registries. The first 4 steps in the workflow are responsible for satisfying the first 2 requirements along with satisfying the requirement for decentralized query storage. The last 2 steps in the workflow are responsible for satisfying the decentralized computation trust and the other remaining requirements. We have proposed a decentralized architecture for a consortium of cancer registries with robust query authentication and authorization framework. Furthermore, we proposed the decentralized architecture framework based on executing multi-party computation protocols via consortium blockchain network to support stronger threat models. Finally, we have conducted informal security analysis to demonstrate the security guarantees of the proposed architecture. Currently, we are building the prototype. In the near future, we would like to finish the implementation of the prototype and do thorough performance and dependability benchmarking study. Furthermore, we would like to do formal security analysis and extend the architecture with additional capabilities to support more security and privacy requirements.